So in this video, we are going to talk about the bivariate regression, multiple variate regressions or multivariate regressions, and we're going to talk about the line nest function a little bit if we have some time left. So let's start with a bivariate regression. Bivariate means there are two variables. One is a dependent variable and one is an independent variable. Now ask yourself this before we start. We have data on age of a person and height of a person. Which one of these two would be the dependent variable? So dependent variable means something that depends on something else. So in this case, does age depend on height or does height depend on age? If you answered that height depends on age, you are correct, which means that our height is our dependent variable, and traditionally we represent that with a y. That means that age is our independent variable and we will be representing it right now with an X. All right, so regression analysis basically takes values of a given variable and takes into account, like in this case, our hypothesis is that age affects height. The older you are, the taller you are. Now, notice that based on the descriptive statistics video we did earlier, we have everybody under the age of 20. So this relationship that we are testing is not entirely wrong. Now, if we were to not have an age restriction, as in this was a general age, right? Like from 0 all the way to 100 years old, then maybe the height function will be very, very slightly connected, because after a certain age, between 18 and 21 years of age, people stop getting taller. So in this case, we can actually estimate this function because the age is restricted to under 20. So let's try to see if we can run a regression. The reason I gave that example about age is that if two things are completely unrelated and you run a regression on it, you're literally just wasting your time, right? So you need something that is meaningful to test for a relationship in the first place. So let's run the regression analysis. We want to see if we can predict the age of somebody within this range, right? Or even beyond a little bit, based on this height and age relationship. So that is the purpose of regression. We use given existing data in order to come up with a way to estimate values for the future or for other people. So we go into the data tab again, go to our favorite data analysis, and we scroll down. We'll see the option for regression. You click on that, click on OK. And again, in this case, I have already tried to play around with it, which is why you're seeing these values. But when you open it up, it's going to look blank like this. Now, the Y range, remember we identified that our Y here is this height. So we're going to pick this and pick the whole range, input X, input X, and here we go. Our first row has labels in them, so we're going to click on the labels, and we want to see our regression results up here. So I'm going to click E1 again. As you can tell, this is my standard way of getting output. Also, we want to pick residuals. We want to show the residuals, and I'll show you what those mean in a second here. So I'm going to click these, and I'm going to click OK. That's fine. I don't mind if they remove the options here. So here is our regression analysis. And you can see these are our predictions. Basically, they are saying that for these 20 observations, the predicted height based on what we got from the regression would have been these numbers. So I'm going to show you this because it's kind of interesting. So I'm going to insert a few columns, and I'm going to take these two and copy, and I'm going to paste them here. All right. Now I want you to see this. According to the regression equation, this person who is 16 years old should have had a height of 59.10, right? And this is the residual, which means that in reality, the person's height was 61 inches, which means that there was a residual or miscalculation of 1.89. Similarly, this person who's 64.5 inches tall was predicted to be 63.69 based on the regression analysis. So what does regression analysis give us? It gives us an R squared, and R squared here is 96.45. They're saying that 96.45% of the variation in the height or variable Y can be explained by a person's age or X variable. That is how to interpret an R squared. And what does our regression equation look like? Well, the intercept is 34.63 and the slope is 1.52. So if you remember your basic algebra, which gives the equation of a line as being equal to Y is equal to mx plus c, or a constant, then basically what you're saying is that Y, in this case, the predicted Y is equal to 1.52 times X plus this coefficient here, 34.63. That is basically what we got. We got a line that predicts what a person's height would be if we knew their age. And that is why regression analysis helps us in terms of predicting things or being able to identify what an expected value would be. The details of regression statistics, of course, will be covered in class, but I do want to say in Excel, you'll often see this capital E show up, especially in things like regression analysis and probabilities. Look here, see those E's? The E represents 10 raised to. It's a scientific method of writing. So if you go in here and see where it says general, and if I put it in a number form, you'll see that it will change, right? 1.68 times 10 raised to minus 14. So basically this number is saying there are 14 zeros multiplied by 1.68. I mean, so before 1.168 shows up. So if you want to see, look, there are 13 zeros because it's 1.68, but so there are 14 points. So when you see that E sign, you can understand that it's a very, 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 very small number. If this number here is negative, right? If this number E raised to negative 14 means it's a very, very, very small number. If it was E raised to 100 or something, that's 100 after E, then it's a very, 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 very big number. So just keep in mind that when you see that E, it is a scientific notation, and keep that in mind because otherwise you will write your answers wrong. So that was bivariate regression. And I want to show you this little function that is designed to help with, instead of running the whole regression, you can get some of these estimates, the key estimates, like the slope, right? See, notice this number here, I'm going to highlight it, and this number here are the same. This number here and this number here are the same. So basically, LINEST allows you to get these numbers directly. And when you run the LINEST function with information, you will see that the residual degrees of freedom, here it is 18, here it is 18, right? So you will see that what you get here is similar to what you're getting here. So I'm going to just I'm going to leave that there, and I'm going to write the linest function again for to help you with it. Linest here, the known y's are again these numbers, comma, known x's are these numbers. Now we want to include the constant, so we put in a true, and we want to include all the stats. So I'm going to put in a true, and here you go. Notice that's how I got these numbers. What do each of them represent? This is the slope. Now that's the problem. If you're using the linest function, you need to know exactly what is denoted by each of these numbers, because Excel does not give it to you. So here you go. The first thing is the slope of the equation. This is the intercept. This is the standard error of the slope and standard error of the intercept right here. Look, these are the standard errors, right? R squared, which is given to us when we run the full regression right here, is given to us. R squared is right here. This is the standard error of the Y. 489.105 is the F value. 18 is the degrees of freedom. And these are the regression sum of squares and the residual sum of squares. Again, regression sum of squares and residual sum of squares. So in this case, we would have to calculate the t values on our own. And the t values is basically taking the slope divided by the standard error, or the intercept divided by the standard error. So if you notice here, slope divided by the standard error. So you have to manually calculate them. And look, this, I'm going to show this because it's kind of cool. Look, this number is the same as this number right here. See that? So that's how we obtain them. So either you run the full regression, or you can use a linest function, as long as you know how to use it. If you don't know how to use it, or you're not sure what is what, always run the full regression, right? So that was bivariate regression and linest function for that. And now we'll go to the multiple regression. I have set up the multiple regression with some more data. So in this case, we're interested in finding out how to predict the weight of an individual. So we're going to have the weight given to us in pounds. This is information on about 25 people that has been collected. Actually, it has not been collected. I just totally made it up. But for now, we are going to pretend that it actually exists. This is how old they are. So we are basically trying to test the hypothesis that weight, or our dependent variable, or also known as our variable of interest, is a function or depends on age, gender, race, and height of an individual. So again, these are the age in years. This is the gender. 0 represents a female and 1 represents a male. For the sake of simplicity, we are going to use a binary gender variable with a 0 and 1. This race variable is, we have graded it from 0 to 4, but this is a qualitative variable, as in there is nothing which says, oh, being Hispanic is better than being non-Hispanic black, or being non-Hispanic black is better than being non-Hispanic white. It's just a number that is representing each race, okay? So you have 0 through 4. These are the categories for the race variable. Height in inches has been considered again. And since only adults have been considered for this, everybody over the age of 20, the heights are randomized based on, between 48 inches and 75 inches. So one option, the first thing you can do, or you should do, is to run the descriptive statistics for all of these and try to get an idea of what these variables mean. I'm going to leave that to you to do on your own. if you want to play around with it. I will try and upload this Excel sheet also into your Blackboard course. So you can do this on your own. And now we are going to run a multiple regression. Multiple regression means that weight depends on more than just one variable, age. Weight depends on age, gender, race, and height. That's what we are testing for anyway. So again, we go into data, go to data analysis, click on regression. Again, this is because I had copied stuff over. All right. And I'm going to input the Y range. I want to include labels. Input X range. Now, you, instead of having to pick each one separately, you can simply get all 4 of them together, grab them. Make sure you say labels. If you do have labels up here, it won't let me change it. Okay. Output range, I want to put the output here in I1. You can also get the output in a separate worksheet. That's, you know, entirely your choice. And I'm going to click OK. Here we go. Basically, the intercept is 51 pounds, negative 51 pounds. The age is 3.43. The slope for the age is 3.43. Gender is 42.94. Race is negative 11.70. Height is 1.82. And then these are the corresponding t statistics and p values. We can see that the intercept is not significant because it's not less than 0.05, but all the other slopes are significant. So, and here's the R squared. 65% or 65.41% of the variation in weight can be explained by the age, gender, race, and height of the individual, based on this regression analysis, of course. So how would you write it out? Well, here is how you would write it out. So y hat, or the predicted y, or the predicted weight, however you want to call it, is equal to negative 51.46, right? Plus, no, I'm just getting these numbers from here, okay? Plus 3.43 times age, plus 42.94 times gender, minus 11.70 times race, plus 1.83 times height. So if you wanted to predict what the weight would be for an individual, you should find out what their age is, what their gender is, what their race is, and what their height is. And then you can plug it in to this equation to predict what their weight should be. So I'm just going to try something out, okay? So let's say that I know a person who is 42 years old, right? Female, Asian, and is 64 inches tall. Okay, so how do I calculate the y hat value now? Well, I'm going to say this number multiplied by, remember I know, this number is the intercept, plus this number multiplied by, the person is 42 years old, plus this number multiplied by, the person is a female, so we know that female is represented by a 0, plus the person is Asian, and the representation for Asian is 3, so multiplied by 3, plus this number multiplied by, the person is 64 inches tall. Enter that in and hit the enter button. The person should be, or is expected to be, 174.399 or 1 roughly 174.4 pounds in weight, based on this regression. Okay, so this is how we use multiple regression. You can also use the line-est function here. I want to show that to you just so that, but I'm going to use a simpler version. Actually, I'll show you both ways. Okay, so first I'm going to pick, this is the y, comma. When you're running a multiple regression, it is important to put the y before the x's so that you can pick them all up simultaneously. So just keep that in mind, right? Constant, true, and then stats. We want to get the stats. Okay, and basically that gives you, these are, and be careful, this becomes the intercept. Okay, that's the last number that's given to you. So the slope of age, slope of gender, slope of race, and slope of height, right? So that is the order in which these are the standard errors for the corresponding slopes. This is the R squared. Notice that's what we got here too. And I always miss some of this. Degrees of freedom is 20 right here. And then we have the sum of squares and F values. This is the F value and sum of squares are given here. So you can use that. I just want to show you, if you want to put a line-est, if you just put a regular line-est function without, so you can do this too. Line-est, comma, and then pick the x values and constant, and then we don't want the detailed statistics. It'll simply give us the corresponding slopes for each x variable and then an intercept. So keep this in mind. You can use the line-est function if all you're looking for is the slope and intercept. But if you want to make sure that, you know, to identify whether they are significant or not, it's always easier to run the regression statistics because you can see very clearly whether they're significant or not. So that is all I have for regression analysis. And I'm going to stop this video here and then I'll work on the next video. All right.